This is example 1.4-4. A force P of 70 newtons is applied by a rider to the front hand brake of a bicycle. P is a resultant of an evenly distributed pressure. As the hand brake pivots at a tension T develops in the 460 millimeter long brake cable with a cross-sectional area of 1.075 millimeters squared, which elongates by delta equals 0.214 millimeters. Find the normal stress sigma and strain epsilon in the brake cable. Alright, so here's a couple things. You can see that we have the brake and it rotates around point A, and we have force P, which is due to an evenly distributed load, so the resultant is in the middle of that distributed load, and then we have this force, the tension force on the cable over here, which is at a distance from A, and we have cross-sectional area. I'm not sure why there's a subscript E, but that's what that is. It's the cross-sectional area of the cable. And then also there's this symbol here, which is incorrect, and it should in fact be sigma, which is the symbol we use for strain. And now let's talk about our givens and finds. So first of all, we are given the force P as well as the length of the cable and the cross-sectional area of the cable. And delta is the change in length of the cable. And we also need to find, or we're given the distance of each of the forces from the pivot point A, and these are the perpendicular distances, which are very useful for finding the moments about the point. And I'm going to call this one RT because it is the distance to A that the tension T is acting on. And then this one over here I'm going to call RP, and since it is a resultant force of the evenly distributed pressure, it will be halfway in between 50 millimeters and 100 millimeters. And so this one is 75 millimeters away from point A. And now I'm going to write out the givens and finds. We're finding the sigma as well as epsilon. And now that we are ready to start working through the problem, we draw our single line to separate the problem from our work. And we are going to go ahead and start with a free body diagram. This is important to help us figure out, or to help us see where all the forces are and how they affect each other. This will help us find force T, which is the tension in the cable. And for this one, it's not super important where we put everything. If you think about it, the brake is basically just something that rotates around point A, and we don't need the reaction forces at A in the x and y direction. We only need force T, and both T and P act around point A. So they are trying to rotate the brake in opposite directions. And so what really matters is just the relative, where the forces are relative to point A and to each other. Basically just their distance from A, which we are given. And so because of this, we just need to do our sum of moments around point A and we don't need to do any sum of forces in the x or y direction. And so once we finish our free body diagram, we will start with that. And for our sum of moments equation, we're going to choose the counterclockwise direction to be positive, and our brake does not have angular acceleration, so this is equal to 0. And then we put in our values, which would be each force multiplied by its distance from point to A. And P is going counterclockwise, which is the direction we chose as positive, so we write it as positive. And then we have our tension force T, which is acting in the opposite direction, so it is negative. And T is the only unknown, so we can rearrange to find our value. And this is equal to 140 newtons. And this is an intermediate answer, so we give it a single underline. And now that we have all the information we need, we can move on to finding our stress and strain in the cable. So for our stress, we use the symbol sigma. And if we remember, this is a force over an area. And in this situation, our force in our cable, that's what the sigma is. It's the stress within the cable. So the force in the cable is our tension T, and the cross-sectional area is our A subscript E, which we are given. And since we were not using meters, we cannot convert it directly into pascals. We're going to have to do some unit conversions. And one way you can think about this is that there are 1,000 millimeters in a meter. So if we multiply by 1,000 millimeters and divide by a meter, this value is equal to 1. And since we have millimeters squared, we're going to square the top and bottom of this, and it will still be equal to 1, so it's not changing our value. And this here, newtons over meters squared, that's pascals, which is what we want to convert to. And then, of course, the millimeters cancel out. So we have 130 times 1,000 squared pascals, and we can convert using the 1,000 squared using our unit prefixes. So the 1,000 squared becomes, or goes away, and then we use megapascals. And that is one of our final answers. And this is a little squished in here, so I'm going to move it just a bit. And since it is a final answer, I need to remember to draw an arrow from the margin and put our variable in parentheses. And finally, we need to find our strain with the symbol epsilon. And this is our change in length over our original length. And this is engineering strain because we're using original length. And we are given both of these values, and so we can just plug them in. And this is equal to 4.65 times 10 to the fourth, or negative fourth. And this is unitless because it is like a relative change, and it makes sense because we have millimeters divided by millimeters, and this is one of our final answers. We double underline it and draw an arrow and put the variable in parentheses. And we have found everything we're supposed to find, so we're done, and we finish by doing a double underline at the end of our work across the entire page.